All right, so we're going to look at what's called the hypergeometric distribution, which is basically when you're sampling without replacement. So for example, balls in a bag, you take one out, and before you draw the next ball, you don't put that ball back in. So we're not replacing it. Here's basically what it says, and obviously it looks very confusing, but our job today is to understand this. It's even hard to read, but the probability that x equals lowercase k is equal to capital K choose lowercase k multiplied by n minus k choose n minus k all over capital N, all over n choose lowercase n. This is just a different notation, which you'll sometimes see. So this function here is what's called choose, and I'll put some links below to explain that in detail because it's fundamental to this distribution that we're going to talk about. All of these letters can be confusing, but sampling without replacement follows a hypergeometric distribution such that for total n objects, so capital N represents the number of objects, where K, capital K, have the property. Okay, X is our property of the thing that we're interested in. It'll make sense with an example. The probability of selecting lowercase k with property X out of a selection lowercase n. Confused? I'm not surprised because it is tricky, but let's step through it. The best way to do this is definitely with an example. So here's our example. A box contains 5 red balls and 3 blue balls. John selects 3 balls from the box without replacement. The probability that exactly one of the balls that John selected is red is. Okay, let's just put all this to the side for now, and let's just think about our tree diagram. This problem could be worked out with the tree diagram, but this is a very powerful tool for computing this solution to this much more quickly, and you'll see why that's the case in a moment. Okay, you would agree in the bag, you could get a blue ball, you could get a red ball. And then from there, you could get a blue ball or a red ball on your second selection. And then from there, you get a blue ball or a red ball, blue ball, red ball, blue ball, red ball. You get the idea. And you get a tree diagram that would look like this, where you either get a blue ball or a red ball as you go along, right? Okay, let's put the probabilities on. But remember, it's without replacement, so the probabilities change. So this is a conditional probability experiment, I would describe it as. So 3/8, because there are 3 blue balls and there's 8 balls in total. So the probability on the first run that you get a blue ball is 3 out of 8. But on the second one, you've already selected a blue ball, so there's only 2 blue balls left, and there's only 7 balls in total left. So it's going to be 2/7. And then finally, if you selected a blue ball on the first and second runs, there's only 1 blue ball left, and there's 6 balls in total. Okay. Similarly, if you selected a blue ball and then a blue ball in the first 2 trials, then there is 5 red balls left, and there's only 6 balls left in total, so you get 5/6 here. So this is how you construct a tree diagram. I encourage you to keep thinking about the rest of them. I won't explain all of them. But again, if you selected a blue ball and then the next one was red, well, the probability that it was red, well, there's 5 red balls, but there's only 7 balls left because 1 was already selected. So there's 5/7 here. And then you go along. I think hopefully you get the idea. Really important you understand this step and how I'm getting these probabilities. This would be 2/6, 4/6, and so on. You fill them all in again from the first draw, 5/8, and you'd get all of these probabilities. Okay, so with this tree diagram, we could actually answer this question because it says the probability that exactly one of the balls that John selected is red. Okay, so using a tree diagram, you could do this. Exactly one is red. So you'd have to get a blue, blue, red. There's one option along here. Or you could go blue, red, blue. You could be there to get one red. Or you could go red, blue, blue. So you could go down there. So if you so calculate each of these branches. So 3/8 times 2/7 times 5/6 plus 3/8 times 5/7 times 2/6 plus 5/8 times 3/7 times 2/6, and then add them all together. You'll get the correct answer. But that can be cumbersome, especially when we've got even more than three trials, when we're selecting like 50 balls. How are we going to work this out? And this is where we need this, okay? So let's break this down. Okay, and I'll just talk through this. So the probability, all right, X is the property that we're referring to. We're interested in this question in the ball being red. So capital X is the situation, or is the random variable where we get red as our outcome. Okay, and we want exactly 1 red. So lowercase k is going to be 1, okay? Probability of selecting k with property X. So we want one that is red. So lowercase k is 1. Okay. All right. Capital K have property X. So 5 have the property that they're red. So it's going to be 5, choose 1. Okay. And then it's capital N minus K. Okay, so that's 8, choose 5. Sorry, 8, take away 5, because capital N is the total number of objects. There's 8 objects. Take away 5. Have the property X, which is capital K. So 8, take away 5. Choose 3, take away 1. All right, lowercase n is the probability of selecting K with property X. So lowercase n, you're making n selections. You're making 3 selections. And then we said K is 1. So 3, take away 1. All divided by capital N, choose lowercase n. Capital N, again, is the total number of objects. There's 8 objects, and you're making 3 selections. So it's confusing, but I think what I'm going to explain next will help make sense of the whole thing. Here is our bag of red and blue balls. Okay, let's think for a moment about how many ways we can choose from the red balls. We're just thinking the red balls now. How many ways can we choose one red ball? Well, I could choose this one, or 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 I could choose that one. So there's 5 ways to select one ball out of, there's 5 ways to select one red ball out of 5 red balls. Okay, so that's essentially, there's 5, choose 1. I just want to explain that in a bit more detail as well. Imagine it was 5, choose 2. Imagine the question was exactly 2 of the balls that John selected is red. Okay, be 5, choose 2. How many ways can he select 2 from 5 red balls? Well, let's explain. He could pick this one and this one. There's one way, or he could pick this one and this one. So there's 2. Or he could pick this one and this one. There's 3. Or he could pick this one and this one, which is another possible combination. And then hopefully you get the idea. You could select this one and this one. You could select this one and this one. You could select this one and this one, this one and this one, this one and this one, and then that one and that one. So that would be if it was 5, choose 2, if the problem asked us to 5, choose 2. And you're like probably thinking to yourself, well, why do we care about that? Well, the reason we care about that is because, yes, that's just a number. How many ways can we choose 2 red balls out of 5? And that's just a number. That's not a probability. But if we were to divide that by the total number of outcomes, 8, choose 3, in this case, then we would have a probability. Okay, so the last thing I think there is to explain is why we do 3, choose 2. Well, from the 5 red balls, we're choosing one of them, which must mean, since we're making 3 selections, from the 3 blue balls, we must have selected 2 of them, because this stuff doesn't happen in isolation, right? From the 5 red, you're choosing 1, which must mean from the 3 blue, you chose 2, if you want exactly 1 red ball. And the reason we're multiplying them is because of what's called the multiplication principle in combinatorics. So I'll put a link for that below as well. And we're dividing by 8, choose 3. Okay, 8, choose 3, I just want to explain that, is the total number of possible outcomes. From these 8 balls, how many ways can I select 3 of them? Well, now we're starting to get into large numbers, right? Because I can select this one and this one and this one, or I could select this one, and this one, this one, and this one. You get the idea. So that's going to be our denominator. That's all total possible outcomes. So I don't know if I explained that very well. That's how I think about it. Hopefully that made some sense. I just want to show you how to compute it. So 5, choose 1 multiplied by 3, choose 2, all over 8, choose 3 is 0.2679. So that's the probability that he selects exactly 1 red ball. If you come to GeoGebra, there's actually some really cool things you can do. There's a probability page. We want a hypergeometric distribution. The population was 8. There was 8 balls to choose from. We took a sample size of 3, and n is the number of successes in the pile, right? And there's 5 red balls essentially. So if we want to know the probability that we get 1, let's change this to be 1 and 1. And that's this, right? This is our hypergeometric distribution, which is pretty cool. So you can see up here, the probability that we have selected exactly 1 red ball is 0.2679. So hopefully that made some sense. It's definitely a challenging idea. It's a bit hard to explain as well, but good luck, and I'll see you soon.